Yes, I welcome you all for another presentation on electronic devices. As we have told or as we have discussed in our previous presentation, electronic devices is a very important and it is a very core subject of electronics and communication branch is concerned. By the way, today we are going to see lecture number 2, right? So, in today's presentation, we will continue the same introduction part of our electronic devices, right? In last presentation, we have seen the classifications of materials basically, right? I will continue the same for your better understanding. Classifications of materials, right? Classifications of materials. So we have seen in our previous presentation is that depending on the energy band diagram, right? Depending on the energy band diagram, the materials are classified into in three broad categories. Those are called, the first one is insulators. We have seen this in the last presentation, insulators, and the second one is conductors, and the third category is semiconductors, right? These are the three broad categories of the materials, right, which are differentiated or defined based on their energy band diagrams, right? Insulators, and then conductors, and then semiconductors. Insulators are the materials which will not allow the current to pass through this material. Thereby, this insulator will have very poor conductivity actually, very poor conductivity, very poor conductivity, right? The conductivity, because there is no conduction process will takes place in insulator, right? And moreover, as I have explained in the previous presentation, the energy gap is approximately, it is greater than 6 electron volt. It is greater than or equal or greater than to 6 electron volt. That is the energy gap of this insulator material. Whereas coming to the conductors, in this the energy gap, the conductivity is very good. So the conductivity is good, right? And the Eg, the energy gas, there is no Eg actually, zero, zero electron volt, because both the bands, conduction band as well as your valence band, both will be overlapped to each other and there will be no energy gap for these conductors, right? And we have seen certain material, I mean a small metallic bar we have considered in the last presentations. From there we have we have derived one important relation between the applied electric field and then the drift velocity, right? That is Vd. Under this conductor, we have seen one important relation is that Vd, drift velocity, is proportional to applied electric field. Thereby, if you remove this proportional, then Vd is equal to mu into E. This is what we have seen. Vd is equal to mu into E. This is called mobility, where mu is called mobility. So this parameter is very important parameter, okay? And this mobility will be defined for both electrons as well as the holes, right? So for electron mobility, it will be represented by mu suffix n. This is called electron mobility, right? And if it is for hole, it is called mu suffix p. Mu suffix p is the whole mobility, right? And right, whole mobility. Clear? So drift velocity is equal to mu into E. Okay, this is what for conductors we have seen actually. And whereas coming to the semiconductor is nothing but, and moreover we have seen one important thing in insulator, the availability of the free electrons N is approximately equal to 10 power 7 electrons per meter cube. Very very important point. 10 power 7 electrons per meter cube. These many free electrons are available in insulator, means very less actually. This indicates very less value of electrons per meter cube. 10 power 7 electrons per meter cube. N is equal to means the free electrons available in the insulator are about 10 power 7 electrons per meter cube. Whereas if you see the conductor, it is approximately, it is 10 power 28. If you see in conductor, no, so N is approximately equal to 10 power 28 electrons per meter cube. So if you see the conductor, the number of free electrons available are 10 power 28 electrons per meter cube, means it indicates very large number of free electrons. Thereby the conductivity is very good in conductors. And coming to the semiconductor, actually the semiconductor is nothing but the material which will have the property between the insulator and then conductors. The material, we can define the semiconductor as the material which will exhibits the characteristics, okay, between insulator and then conductors. Those are called the semiconductors, right? Semiconductors. So as far as your semiconductor is concerned, the energy gap EZ is approximately 1 electron volt. The approximate, okay, semiconductor, the energy gap for this semiconductor material is about 1 electron volt actually. And similarly, if you see the number of free electrons available under this semiconductor, the number of free electrons available in semiconductor N is equal to approximately, it is greater than 10 power 7 electrons per meter cube and then less than 10 power 28 electrons per meter cube. This is the range of the free electrons available in semiconductor material. It is greater than 10 power 7 means above insulator, and then less than 28, 10 power 28 per electrons means less than conductor, which indicates that the semiconductor will have the property in between insulator and then conductor. Okay, these are the very important points to be remembered actually, right? And let us see one more important aspect and one more important parameter, electrical parameter with respect to the conductor. Then we will move for the semiconductor actually. So in the last presentation, if you remember that, we have considered one metallic bar actually. Okay, so we have considered one metallic bar and we have applied some electric field here, right? Then it is E is the applied electric field actually, and we have seen that this is something, let us say it is a valence band and let us say it is some conduction band, and in valence band we have some amount of electrons will be there, and now these electrons basically you can represent like this, no problem. So these electrons, we have to make these electrons to move from valence band to conduction band by crossing this energy gap. Whatever the energy gap is there here, so they have to, okay, travel through this. They have to cross this energy gap actually. Clear? So the velocity with which the electron moves from valence band to conduction band, that is called drift velocity, we have seen actually. Okay, that is drift velocity, and drift velocity is proportional to electric field, applied electric field, and Vd is equal to mu into E. This relation we have seen. Now let us say for example, these are the free electrons available in valence band. Assume that, so n is the concentration of, if small n is the concentration of free electrons which are there in the valence band, okay, right, and q is the charge of electron, n is the concentration, q is the charge of electron, then we can define the conduction current density. We can define one important parameter here is that the conduction current density. Conduction current density. Current density is nothing but J actually, right? Current density. You already aware of this actually, right? So what is the current density basically? In general, anybody can, let us say for example, any copper wire, let us say it has some length L is the length of the wire, and okay, let us say some current flowing through this and it has some cross sectional area, okay, this is some copper wire, or some conductor actually, it is some copper wire, it has certain cross sectional area A. Assume that L is the length of that wire and I is the current flowing through that. There you can define the parameter is J is equal to, means current density, that is current per area, cross sectional area. This is what the basic definition of a current density, and this current density is called as conduction current density. Conduction current density. We have to current density. Sometimes what we will see, you can remember this J as most of the time like a current density only, but you must remember as not simply current density. This current density is called as conduction. That word you need to remember. Conduction current density. What is the units of current? It is ampere per, what is the area? It is meter square. Amperes per meter square is the SI units of the current density J. Right, you need to remember the units also. So J is equal to I by A. I is measured in amperes and A is the meter by meter. Meter square means length by breadth. Length is meter, breadth is meter. Meter by meter area, meter square, ampere per meter square. This is normal or general definition of a conduction current density, that is I by A. Okay, let us remember at this moment. But here, as far as this metallic bar, whichever we have considered here, with respect to that, we can define another kind of definition of J, conduction current density J is equal to the concentration of electron into charge of electron into drift velocity. This is another important form of definition of conduction current density, right? J is the conduction current density is equal to N is the concentration of electron, Q is the charge of electron, Vd is the drift velocity. Therefore, N into Q into Vd, if you multiply these three parameters, then you will get the value of J, and that is called conduction current density. And if you expand little bit more this for expression to further, you will get, I write here for your sake of understanding, right? It is J is equal to N is the concentration, Q is the charge, Vd is the drift velocity. And further this can be written as N into Q into, what is Vd? Mu into E. And further this can also be written as sigma E. This is J is equal to sigma E. Very, very, very important relation where sigma is equal to N into Q into mu. This is called sigma. Sigma is called conductivity. Sigma is called as conductivity per ohm meter. per ohm meter. That is the unit, per ohm meter. Conductivity SI units. Per ohm meter is the SI units of conductivity. Therefore, here N into Q into sigma mu, N into Q into mu is called as sigma, sigma into E. Therefore, this relation is called as the Ohm's law of electricity. This is called Ohm's law of electricity. As per the Ohm's law, therefore, the conduction current density is directly proportional to the applied electric field, right? The conduction current density is directly proportional to the applied electric field. Means, if the field is more, then conduction current density will also more. If it is less, then the conduction current density will be very less, right? So this is what the Ohm's law expression from this conduction current density, and this is the conductivity NQ mu basically, right? So this much we need to remember here. Now coming to the semiconductor, the third classifications of the material, that is the semiconductor. Semiconductor is nothing but the material which will have the properties of, okay, in between the insulator as well as the conductor, then that material is called as semiconductor. Okay, so if you see the energy gap of this, basically energy band diagram of this semiconductor, so it will be, this is your conduction band. Let us say this is what your valence band. This is VP in general, valence band. This is what your conduction band, let us say, and the gap between these two bands is E, is approximately 1 electron volt. That's it, 1 electron volt. The gap is very less. Basically, right? The gap is approximately 1 electron volt. And similarly, the availability of free electron, I already told that it is greater than 10 power 7 electrons per meter cube to it is less than 10 power 28 meters, electrons per meter cube. In between, this is what, okay, this is what the availability of free electron in semiconductor, right? And the most very important examples of semiconductors are silicon and germanium. These are the two very important practical examples of semiconductors are silicon and germanium, right? So, and silicon and germanium, these two will have certain similar properties actually. These two will have certain similar properties. That's why these two are selected for semiconductors actually, right? If you see the silicon, what is the atomic number of silicon? Okay, consider the silicon. Okay, what is the atomic number? So the atomic number for silicon is 14, is it not? Now this is the atomic number or atom number 14. If you write the electronic configuration for this silicon, and obviously you can write like this, actually it is like 1s2, 2s2, 2p6, 3s2, 3p2. That's it. This is what the electronic configuration of silicon. So if you see this now, 2 plus 2 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 2 is 14. So if you sum all these, okay, power, the values in power, then all must equal to 14. Therefore this is electronic configuration, right? If you see, this is the first orbit, second is these are the second orbit basically, second orbit, and the shell, S shell and then P shell. This is the second orbit. and this is the third orbit basically. In third orbit, okay, you know that. So the S shell, the maximum possible available of electron in S shell is 2 only. The maximum electron can be 2 only in SSL. Okay. Similarly, P, for the P shell, the maximum electrons, the capacity of the P shell is 6. Right. So if you see the first orbit, in first orbit only you have SSL, and that is completely, it is stable actually. Coming to the second orbit, in second orbit you have S shell as well as P shell. So S is almost all, it is completely filled, means the capacity is 2 only, therefore it is completely filled. And P cell, the maximum capacity is 6 only, 6 electrons, it is completely filled, therefore it is also in stable condition. This is also stable condition. Your first orbital is stable, second orbital is also stable. Coming to the third orbital, basically in third orbital the S shell is occupied with 2 electrons, it is okay. Whereas coming to the P, what is the maximum, the capacity of P is 6, so it can be up to 6, but we have only 2. Therefore, it means that the third cell, whatever is there, the third cell is something not stable, it is unstable. It is unstable. It is unstable. Means that, so in the third orbital, what are the electrons available? 2 plus 2. Because both are there in, though it is S shell and P shell, but both are there in the third orbital. Therefore, the orbital itself, it is a unstable condition. That will be an unstable condition. Therefore, how many electrons are there? 2 plus 2. Totally, you have 4 electrons here. These 4 electrons are called as valence electrons or free electrons. Okay, these 4 electrons are called as valence electrons or free electrons. This is as far as silicon is concerned. Coming to the another beautiful example, that is germanium actually, germanium. And the atomic number of germanium is 32, right? Germanium is 32. Write the electronic configuration for 32. How it could be? So if you write the electronic configuration for germanium, it is very simple. It is 1s2, it is 2s2, it is 2p6, right? It is 3s2. Is it not? 3p6, 3p6, 3d, 3p6, then 3d, 10. After that 4s2, 4p2. Clear? So this is the electronic configuration for germanium. So if you sum all the values there in the powers, 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, 18 plus 10, 28, 28 plus 2, 30, 30 plus 2, 32. Therefore, 32 electrons are there, it is nice. Then coming to again here, this is the first orbital. In first orbital, you have S shell and the maximum capacity is 2 electrons only. Therefore, in S shell, the maximum 2 electrons are there. It is completely stable. First orbital is stable. Coming to the second orbital, this is the second orbital. In second, you have S shell, P shell. Then in S, the maximum is 2 and P is also, the maximum is 6 electrons. Therefore, it is occupied, it is completely filled as per their capacities. Therefore, it is also stable. Coming to the third orbital, in third orbital you have S shell and then P shell. In S shell the maximum is 2 electron, in P shell maximum is 6. Therefore, these two are filled with their respective maximum values. Therefore, the third orbital is also completely stable. Coming to the even the 3 also, not only this, you have 3s, 3p, 3d also. So the maximum d orbital is also 10, d shell. So the d shell is, the maximum of d is 10. Therefore, it is completely stable here. Coming to the fourth orbital, in fourth orbital, if you see, the s shell is filled with 2 and p is again here partial. S is okay. The maximum capacity of S is 2, but the maximum capacity of P is 6. But it is filled with 2 only, means it is filled partially, it is filled. Therefore, in the fourth orbital, if you see in the fourth orbital, it is something unstable actually. This is not stable, this is unstable. Therefore, here what are the electrons in this unstable orbital? 4 electrons. Therefore, here 4 electrons. Therefore, just you compare the silicon with the germanium. In the silicon, the free electrons, free, how many free electrons are there? 4 electrons, and these 4 electrons are there in the third orbital for silicon. Whereas come to the germanium, in germanium also again you have 4 valence electrons, free electrons, they are there in the fourth orbital. For silicon it is in third orbital. For germanium it is in the fourth orbital, no problem. But how many electrons, free electrons are there in both of the cases? 4 only. Therefore 4 electrons here for silicon and 4 electrons for germanium. That is why the silicon and germanium are called, these are called tetravalent atoms. Therefore, silicon and germanium are called, these are called tetravalent, right? Tetravalent atoms. These two are called, both silicon as well as germanium. These two are called tetravalent atoms because both are having same amount of free electrons. Those free electrons are called as the valence electrons, right? So this is about the silicon and then germanium, right? And I think we will finish off this presentation here, and we will continue with some more electrical parameters of these conductors, and with a beautiful topic we will see in the next presentation. I hope you understood well this concept, right? And have a beautiful day. Thanks for watching this video, and if you have any clarifications required, or if you have any kind of things, you not to forget to post on my channel, and definitely I will try to meet and I will try to give the better and best examples or answers for your observations or questions or doubts, whatever you have, right? So we'll continue and we will meet in the next presentation, right?